Week's video. This week we're going to be talking all about the heart. And so, a little space there. So we start talking. We're going to start talking about. Um, First off, I'll pull up a couple graphs here. This graph is going to represent our autorhythmic cell. And a process that we have going on here associated with this, we'll take part of a heart cell. It's connected to other cells here. And draw this graph. This graph looks like this. We have different parts going on. 0, 4, and I'll teach you a little bit about it. So in step 4, a few different channels going on here. These are called funny channels. Funny channels. They're called funny channels just because of the way they act. They act a little bit differently than a lot of other channels. What comes in through here is some sodium. And we have a few other channels going on here. We have a voltage gated calcium channel. And this actually makes up step 0. So inside this we have the smooth plasmic reticulum. There's some calcium in there. And what this does is this calcium channel opens, sends this calcium here. What it does is it actually activates another calcium channel for the calcium in the smooth endoplasmic reticulum to leave, and that will actually activate a potassium leak channel here that will enter the cell. This will be number 3. So we have 4, 0, and 3. So as 4 comes in, we'll talk about it again. The sodium comes in with the funny channels. That does is it activates the calcium to come in. And then the calcium goes to the smooth endoplasmic reticulum, opens that up. What that does is the calcium comes out, activates this potassium channel. And that potassium channel leaks it down under threshold again, and it goes back into step number 4. The way that cardiomyocytes operate is a little bit differently. So I'm going to draw a similar image here. Looks a little bit different. It comes down and comes back down like that. So we have a similar process happening here. With step 0. Sub-0 would be right here. As that comes in, it's actually that sodium again. Comes in, it activates this potassium chloride channel. Oh, I'm sorry, I messed this up a little bit. So this is actually a T-type calcium channel. And it goes and activates as RYR. And once again, we have calcium inside endoplasmic reticulum. These circuit pumps. And as the calcium leaves, a couple places for it to leave, it creates a belong that goes down and communicates with these other cells. So we'll depict this out. Oh, I forgot about this. We get the potassium coming out. So we started out with a little bit of sodium. As that potassium leaves too, then we start these. There's some other channels here. So we have a ultra fast potassium channel, ultra rapid and then a slow. So I was correct when we were talking about this. We have I drew this a little bit wrong. There's a little bit of a peak coming up here. And right here, this is where that L-type voltage gated calcium channel comes in. And here, it starts going down. We call this an inward rectifier. AK1. That's 4, 0, 1, 2 is right there, 3, and 4. So as this process happens, That's what makes our cardiomyocytes. Now we're going to talk a little bit about our waves. Okay, so we have a cell here, or not a cell, we have a heart. And as a heart, we have some different, well, the way that a heart works is it has these different bundles. There's the bundle of His, this is the SA node. What the SA node is, it sends a contraction, particle of electricity down to the AV node. What we're going to do is we're actually going to show you a graph that you typically see in movies. This is how people tell somebody's heart is still beating. So the way that these different parts of the heart here, we have the atrium, we have the ventricles, and this SA node is going to send a signal over. I'm just going to start here on the atrial side. So is it going to look like this? It's kind of flat. This has this little bump right here. Call this the P wave. And as that signal keeps going down, there's all except this side piece right over here, and this will make up the next part. This is the Q, this is the R, and the S wave. And lastly, as it goes over here, it goes to this part. It's called the T wave. And so if we're going to go ahead and label this, we have the atrial, ventricular, and the repolarization parts of our heart. All right, so when we're looking at this EKG, the EKG can tell us a lot about the heart. So I'm going to tell you about when the EKG would perhaps tell us something other than the heart is working correctly. So in the heart, we have the side of it here in the septum, and septum, and then the wall. This would be the wall of the ventricle, wall of the atrium. We have some other coronary vessels that come around, and they supply the heart with this oxygenated blood. And so what can happen is we can build up a little bit of plaque in there. What this does is it squeezes it off and makes it not, makes the blood not get as much oxygen as it needs. And so as we talked about this before, there's a negative charge over here, positive charge over here. We create a vector. So the rule, so this would have a negative tail. The rule when we have this EKG is if it has a negative tail going to a positive, it will create this EKG, this normal EKG. But if it has an opposite effect, it'll look a little bit different. And so we have a couple different scenarios that can happen. and this all comes from this coronary artery getting all blocked up. And what it does is it creates a separation of charge. And so we will soon have a separation of charge here in our coronary vessel. So as this comes through, there is a little bit different of an effect. We have things going this way, and ultimately kind of messes with the charge. And so what this can do is it can actually make this look a lot like this. So we still have our P, our Q, our R, and then our S, and then our T is right here. We call this an ST depression. And this is a sign of an N STEMI, which is an almost STEMI. And then it can continue to occur, and what happens is, so that mainly happens when we just have a slight separation of charge, and it messes with it just a little bit. But as it continues, like I previously drew here, as it continues, we actually have a big effect. Let me redraw that. So we have our P, Q, R, this is S, this is T. And as you can see, S and T are both pretty far above the starting point. This is called an S and T, ST elevation. And this is a sign of what they call a STEMI. And this is a for sure sign of myocardial infarction, which is a heart attack. This is something that doctors evaluate pretty seriously and look at, because this is a leading sign of heart failure. Because the heart, as well, is a muscle. If it does not receive the nutrients it needs, it'll fail as a muscle, and it's a pretty big deal when your heart fails. Next, we're going to talk a little bit about a few different things that can affect the heart, and this is in the long run important for us so that we understand how the levels of the heart go up and down. So we have a few different names for them. So we're going to write down some definitions. Inotropic. It is meaning there's an increase of the strength of contraction. Lucinotropic. It is meaning that there is a decrease in the duration of contraction. And what we're going to be talking about is these are catecholamines and their effect on the heart. So, if you remember, we talked about catecholamines a while ago. Cholamines. This is referring to things such as epinephrine and norepinephrine. And they will bind to adrenergic receptors. And so, these adrenergic receptors that we're going to be talking about in the heart are mainly beta 1. So, I'll draw this in a very simplified manner. Epinephrine is norepinephrine. I believe Okay, so this binds to the beta 1 receptors. And they will activate cyclic AMP and cyclic AMP will activate a phosphorylator. I'm sorry, can't speak. That phosphorylator is protein kinase A. And this has two main effects. It results in the phosphorylation of voltage-gated calcium channels, which are open more, increases in the time it's open, and this results in an increase of calcium from the extracellular fluid. On the other side is phosphorylation of phospholamidin, which increases calcium ATPase. On sacroplasmic reticulum. And what this does is it also has two effects. There's more calcium stored in the SR, and this actually comes and connects because that the calcium from the ECF does come and is stored in the SR. And what it also does is it also helps the calcium to release. Calcium has a huge impact on the heart, as the heart is a muscle, so we have more forceful contraction. The other effect that calcium ATPase has on the sarcoplasmic reticulum this calcium is removed from the cytosol faster. And just a reminder that's using circuit pumps. And this will shorten I-type troponin, in which the calcium binds which will give us a shorter duration of contraction. Okay, so we'll walk back through that. So, as norepinephrine and epinephrine act, they bind to the beta-1 receptors, which activate CAMP. CAMP is then activates protein kinase A, which increases and opens up these voltage gated calcium channels. They're open for longer. They let in more calcium from the extracellular fluid. It also phosphorylates phospholamidin, which activates calcium ATPase on the SR, which in turn results in more forceful contraction and shorter duration of contraction, which this would increase in heart rate. So we have this other cycle that is very similar to the last one that we talked about. This one is called chronotropic. And this one has all to do with the increase of the heart rate. So, once again, we have beta-1 receptors being stimulated. That does is it increases adenylyl cyclase, which increases cyclic AMP, as we talked about before, which increases sodium and this increases the steepness of the slope, which in turn increases heart rate. There's also another turn here off of cyclic AMP. Cyclic AMP, it as well increases pKa, which we just talked about that. Protein kinase A increases that calcium influx. It increases the steepness of the slope again. Makes a threshold or negative. Just once again talking about the separation of charge. Both of these result in an increased heart rate. Next, we're going to talk about the negative chronotropic actions. And this is all caused by acetylcholine. So, as we talked about before, acetylcholine, it has a lot to do with the parasympathetic nervous system. and the stimulation of muscarinic receptors. So M2 is one that functions on the heart. So it affects the alpha subunit. And then the beta gamma heterodimer over here. What the alpha subunit does is it decreases CAMP. On both of these sides. What a decrease in CAMP will lead to is a complete opposite. We will have a flattened slope. This will increase, it will open root channels, which are G protein activated inward rectifying potassium channels. So, as it allows that potassium to enter the membrane, potential is going to be more negative, which is in turn going to decrease the heart rate because we have less action potentials going through the heart. So as the slope is flattened, it also decreases in the heart rate. And this decrease in CAMP over here is going to make the threshold higher. It is also going to result in a decreased heart rate. What we now have to talk about is this whole process of the heart and how it contracts, how it works. What is important to know about that? What we are lastly going to talk about is the heart cycle, the cardiac cycle. This is important to know. Your heart just beats by itself all the time. It's important to know a little bit about why and how it beats. So it starts off, we have these two different graphs. This one is time. This is pressure. We'll be looking at time versus pressure and volume over time. There's a few different segments we're going to look at. Different little dividers I'll make here. What these dividers tell us, they tell us the difference between diastolic, diastole, and systole. And so it's something that we can understand as we look at this graph. So this is our mitral valve closing. As it closes, all of that blood smacks into it and it makes a whoop sound. And as that closes, the pressure builds up, it starts falling, it keeps going down. We're about at the same place until mitral valve opens. So it begins again. And here, so as we read a heart rate of 120, 180, this pressure comes over, it'll hit, come down. And this right here, this is called the dichotic notch. And at this point right here, this makes the dub sound. This is the sound of the semilunar valve closing. I'm sorry, I haven't done a good job of keeping up with this graph down here at the same time. But it starts out higher. As the mitral valve closes, we're going to open up that semilunar aortic semilunar valve. And we're going to send blood out of the heart. And here, it closes again. Closes right there. As we saw right above us, the mitral valve opens again, allowing more blood to come into the heart until it closes once again. So we're going to label a little bit of this. This is called isovolumic contraction. And this isovolumic, iso meaning same, volumic referring to volume. This is when none of the when the mitral valves are both, they're closed. There's nothing going on there. And then we have ejection. As the pressure lowers and also the volume lowers. We have this at first, the systole, atrial systole.